Hey there, welcome back to another video. So in the previous video, we gave a brief introduction of asymptotic analysis, and we also talked about runtime, so these notations, big O, big theta, and big omega. And in this video, we're going to use a more practical example because in the previous videos, we gave some simple code snippets to illustrate the idea of runtime. So in this video, we're going to actually write a solution to a problem. So what I want you to do is I want you to write a function that takes in n, which is an integer, and returns the number of factors that n has. So if n is 12, the factors are 1, 2, 3, 4, 6, 12. So there are 6 factors, so the function should return 6. If the number is 21, we have 1, 3, 7, 21. So there are 4 factors, so our function should return 4. And if we have 100 for n, we have 9 factors, so our function should return 9. Okay, so quickly take a minute or two to write up a quick solution. And then afterwards, we're going to analyze the runtime of our solution and then see if we can come up with a better solution, a much more efficient solution. Okay, so we're back and now we have our solution written, and you probably did something similar, and that is to see if a number is a factor of n, all you have to do is take that number and you take n mod with that number, and if the remainder is 0, that means it is divisible by that number. So in this case, we are checking all the numbers from the range 1 to n plus 1. So this includes n itself, and it starts at 1. You don't want it to start at 0 because you're going to get a 0 division error. You can't divide by 0. So basically, we're going through each number from 1 to n, and we're checking to see if that number is it can be divided by n. So if we put in 12, we're doing, can 12 be divided by 1? Can it be divided by 2, 3, 4, all the way to 12? Okay, so what is the runtime of our solution? And I'm going to run the code just to show you that it works. So we get 6, 4, 9, which is what we have here, 6, 4, 9. So to start off, we have a running total that we're going to return. So this is constant. And over here, we have a conditional statement. Inside the conditional statement, we are doing modulus as well as doing equal, which is equality. So this is constant for the conditional statement. And within that conditional statement, we have an addition. So this is also constant. So we can say that this conditional statement is constant. It is O of 1. Okay, so how many times is this inner block repeated? Well, we're doing this check for all the numbers between 1 and n. So this for loop repeats n times, and it's repeating this check n times. So the for loop runs n times, so the whole thing is O of n. So we have a linear solution. Now, can we do better than linear solution, right? Because what we have here is what we call a brute force solution. Basically, a brute force solution is a solution that is very easy to come up with, but is not the most efficient in terms of runtime. So let's take a look at some of our examples. So if you look at the last factor of any number is always itself, right? What is the factor before that last factor? In this case, 12, the number is 6. And in the case of 100, the number is 50. So it's about half of the last factor. It's about half of n. And if you look at 21, it is an odd number, so it's not divisible by 2. Therefore, if it's not divisible by 2, the last factor is going to be a number lower than half of what that number is. So in this case, it's 10.5 for 21. Second to last factor is going to be less than 10.5 if it's not divisible by 2. In this case, it is 7. This applies to any odd numbers. So if you think about it, we actually don't need to check all the numbers. We can just stop at the half point. So for 12, we can stop at 6. For 21, we can stop at 10. And for 100, we can stop at 50, right? Because the last factor is always the number itself. So we can just start at 1 for num, and we can just stop at half of n. And if I run my solution, we get 649 like we want it. So what is our runtime now? Our runtime is going to be, well, it's going to iterate instead of n times, it's going to iterate n over 2 times. And asymptotically, this is still linear. Even though it is an improvement of our solution, it is still linear. So is there, a solution better than linear for this problem? Well, let's take a look again at our numbers, our examples here. What do you notice about factors? Every factor comes with a pair, right? Every factor comes with something called a complement. So in this case, 1 is paired with 12, 2 is paired with 6, and 3 is paired with 4. With 21, 1 is paired with 21, and 3 is paired with 7. With 100, we have 1 and 100, 2 and 50, 4 and 25, 5 and 20, and 10 with itself. So every number, every factor comes with a complement. So therefore, when we're going through each number and we're checking to see if it's divisible by this number, so if n is divisible by 1, we know that n is also divisible by another number. So in this case, we have 1 and 100, 2 and 50, 4 and 25, 5 and 20, and then we have 10 and 10. We can pretty much stop at 10, right? Because after we get to this point, we're just doing extra work. Because, well, do we really need to check to see if it's divisible by 20 if we already checked to see that it was divisible by 5? If it's divisible by 5, then we can check to see if the complement is equal to the factor, right? So this would, it would eliminate the issue where 10's complement is also itself. So in this case, if we look at 12, we get 1 and 12, 2 and 6, 3 and 4, and then we stop there. We stopped at the halfway point, right, of our list of factors. We're done. We don't need to check anymore. So this halfway point is the square root of the number itself. So in this case, the halfway point for 100 is 10. After we get to 10, we don't have to check any number after it. Whereas for non-square numbers, the halfway point would be the square of the number, and then we'll just convert that to an integer. So we could either do a floor division or we can just take the ceiling of that number. So in this case, what is the square root of 12? Well, it has to be somewhere between 3 and 4, right? Because 3 square is 9, 4 square is 16. So it has to be somewhere between 3 and 4, and we can stop before this point. And what about 21? Well, this is a number between 4 and 5, right? So 16 and 25, 21 is in between those two numbers. So the square root of 21 has to be somewhere between 4 and 5, which is this halfway point, and we can stop at that number. Okay, so to write our solution, we put num back to 0, and then we go from 1 to math.square root of n. So I'm going to import math. You can also do n to the power of 1/2, or you can also say n to the power of 0.5. Either of these work. So I'm just going to use the square root function. So we're going to take the square root, and remember, square root returns a float, so we're going to convert this to an integer. So now when we do this check, if it's divisible by I from the numbers of 1 to square root of n, we're going to make another check. We're going to check the complement. So if n divided by I is not equal to I, so it's saying if the complement is not equal to this current factor, then we make an additional addition. So basically, starting from 1, right? 100 divided by 1, that is a factor. So we add 1 to num, and we check to see if the complement, which is 100, is the same as 1. It's not. So you add another 1. Same thing for 2 and 50, 4 and 25, 5 and 20. And then when we get to 10, we do 100 is divided by 10. So we just add 1, and then we check the complement, which is 10. 10 is equal to 10, so we don't want to double count here. Okay, so now if I run my program, we get 649. All right, so by doing this, we've shortened our runtime. So instead of checking n numbers, instead of checking n over 2 numbers, we are now checking square root of n numbers. So therefore, our runtime is square root of n. So it's O of square root of n. Okay, so that's it for this example on runtime analysis and working on improving our algorithms, making them more efficient. So just to reiterate, we start with linear, then we've improved it a little bit by having the number of iterations. So we start with n, then we had n over 2, but both are linear. And then we found a better solution, which is square root of n. So that is O of square root of n. All right, so that's it for this video. And I hope you enjoyed this video, and I'll see you in the next one. Bye bye.